Hi, thanks for introduction. So I'm Kacper, and I would like to talk a little bit about vector databases. So maybe let's start with some small survey. Who heard about vector databases? Okay, so not a lot. And how many of you use that in your project? Okay, what happened? Was it me? It was me? I'm not sure if I can have control over that. Okay. Okay, as usual, some technical difficulties. Okay, we're back. So vector databases. So for everyone else who didn't heard about that, so basically vector databases, like if you just look into the key features that this type of databases have, so basically the data is stored in something that's called high dimensional vector. So when you look into the relational databases, usually it's data table. In case of the NoSQL databases, the structure is slightly different. Maybe it's a document, maybe something different. But in vector databases, the base structure for keeping the data is high dimensional vector. Each vector that keeps the data is a representation of the one parameter or feature of the data. And basically what we have in the computing, so in case of the basic simple query that we use in the relational database or NoSQL databases. So basically we are looking for something for an exact match, or we're using the like query to get something close, skipping some kind of pattern. But vector databases return results that are the best match for from many features, but doesn't mean that they don't have to fit, or even they have to be as close as possible to the results. So basically they return us always something if we make a query, but it doesn't have to be the exact match that we are asking for. And the last feature that vector databases are let's say announced as is basically the data is stored in optimized data structures. So in comparison to anything that we want to increase the performance of the searching, usually it's we are sacrificing the memory to just receive the data in a high performance way. So let's start from the first. So what does it mean basically that we store the data in the high dimensional vector? Because usually it's very hard to imagine something that is in a higher dimension. It's quite easy to write to draw a cube on the piece of paper. With the hypercube, it's hard. You have to use your imagination. So let's look into the two-dimensional vector. So supposedly we have data that contains two features or two parameters. One of it will be like the size of the element, and the second one will be the color. So right now, we have a couple of elements called A, B, E, and C. A is medium brown, B is small black, large is large black, and C is white large. So right now, if we like to store this kind of data in a relational database, we'll have two columns. One will be named size, the second one will be named color. And we want to execute the query, so we'll just select the data where size is equal, for example, medium, and the color is equal black. And the relational database will return us the element A. If we ask for a medium and black, then the relational database will return us nothing, because there is no element stored in our database in the table that matches both of these parameters. In case of the vector database, if we ask for medium black, then it will return us the closest elements that are matching our query. So in this case, they will return us two elements, A and B, because the A element matches in color, and the B element, excuse me, A element matches in size, and B element matches in color. So in this case, like we will be returning two elements that are the closest to expected results that we are looking for. Before we, let's say, move to the next section, so I would like to remind, maybe tell somebody, if he doesn't meet this, with these three markings, big O, omega, and theta. It's just like notation that describes the complexity of the algorithm. Sometimes it's used to describe the complexity of time of execution or complexity of the memory. The big O notation is a worst case scenario, omega is a best case scenario, and theta notation is the average case scenario. So just some example just to better, let's say, remind ourselves what does it mean. If you look into bubble sort, which is one of the worst sorting algorithm, but everybody implemented that, I think, in their past. So bubble sort has a power of 2 complexity. It basically means that we have to perform power of 2 number of comparison, or the function for the time complexity is basically power of 2 to finish and receive result of this algorithm. For a merge sort, which is more optimal way, it's n log n, which basically means that the complexity is basically less complex. So in most cases, this algorithm will execute faster than bubble sort. So in general, like the simplest and less complex function is the better, because the algorithm is working faster. So if you just try to compare relation database and vector databases, so if you look into the complexity of the insert, the basic relation, both of these databases have the complexity which is described as odd 1, which basically means that we have a constant time of adding element. But in the relation database, we need to allocate some time of generating indexes to receive basically the have the ability to search for the element for a table, for a column that we wanted to search for. After each insert, maybe you have some different policy, but we don't want to look for this element, we have to allocate this time. In case of the search, so it depends. Like on the basic level, we have the complexity in the relation database, which is linear. So in the worst case scenario, we have to look for the whole database, and the element will be found as last. If you use indexes, it can be logarithmic, or basic. It depends also on the policy of the database that using the indexes. But in, let's say, most cases, it's logarithmic. But as I said before, the results of the search is exact. So we just found the element, maybe we found a couple of elements that matching exactly the query, or we receive nothing. In case of the vector databases, the complexity is logarithmic. So we don't have the linear, we don't have to generate indexes because it's, let's say, out of the box. And it returns approximate matches. So if you don't find the exact match, it will return something that is as close as possible based on our database. And in case of the removing, if you wanted to remove some element from the data table, so in case of relational database, so it's similar, that we have to basically find the element and then remove that. So in the vector database is the same. So we want to find the element, so we need this logarithmic complexity. We have this logarithmic complexity to find an element and remove that. Okay, so basically why I'm talking about that and why we are talking about that right now, because it can be used basically for ChatGPT clone. because ChatGPT, as an application, it's using a large amount of data that we have to basically search in. It's complicated than a simple query, but still we have a huge amount of data that we have to browse with some condition. And vector databases is basically one of the key elements that can help us to build something like that. If you look into the tasks that ChatGPT has to done, so basically we have an application that, first of all, we see an input. And what differs ChatGPT from, for example, chatbot, that is general purpose. In case of the simple chatbots that we have, maybe they are not some very simple, but when you look into the chatbot, they are more or less one of, let's say, they have a limited number of tasks they have to do. So we call for a doctor, they want to identify us, so we can provide our identity number, maybe some simple survey, what are we calling for, and then they just redirects us to the specific doctor that we want to talk to, and he already knows who we are, maybe he has already access to our medical record, so we just simplify and shorten the time that we need to speak with human in this case. But in case of the ChatGPT, we basically don't know what is the context when you start talking about what we are talking about. And first of all, we have to basically process what user is put into the input, and then we can finally start doing some action to just learn if you wanted to know about the facts, maybe they wanted to generate some rejects for our application, maybe learn something else. So basically from the let's say program point of view, so everything that we put into the input is basically chaos for our application, and we wanted to process that, so we just put the dots out of this chaos to just extract these pieces of information that is understandable for our program. And then if we have these points, these dots, we can find the best matching answer. So based on what we ask for this ChatGPT or our application, if we have already these dots that is understandable for our program, then you can find the best matching answer. So supposedly we, for example, ask for a highest building in the world. So if we already distinguish that we are asking for a highest building, we are asking that this is highest building not in the Europe, not in the Poland, but in the world, then we can connect these two dots into the fact, which is the biggest building in the world, and then process with the answer. And then at the very, very last, because we are speaking with something that speaks closely to human-like, we want to create a unique human-like answer, which is basically taking these dots, taking these connected dots, and just generate something that is unique and readable for most of the people. But especially this first part, so basically we have a lot of possible questions if we have something like the database of this question. And if we can somehow standardize this question, because there's a lot of ways that we can ask a question about this building. We can just ask to fill out our sentence. So the biggest building in the world is, and just just clicks enter, and the ChatGPT will also react to that to just return us the facts. So there's like multiple ways that we can ask the same question and expect the same result. So this basically is where, for example, vector databases are really come in handy, because we can standardize, understand what our user asks us to do, and then return us the correct answer. So I would like to just show you how you can do that using the Pinecone. Pinecone is like the service that provides the vector database in case of the testing. And the first database, vector database, is basically free, so you can use that. I think that it's when it's inactive for 14 days, it's disabled, But if you wanted to just check that and just play with it, so the pinecone is your guy. So like it looks very similar to what you are doing when you connect to the different database, but there are some differences. So first of all, like we have the structure that provides us as the types. So first of all is like the vector. So basically is the structure that we wanted to save into database, and this will be like this normalized parameters saved in the machine-like or machine-understandable form. And the second thing that we need is something that will transform what we are writing for the user, or just wanted to save in the database, to this understandable by the vector database structure. So I will use the Xenova, which is like the NPM library. In this place, you can always use basically ChatGPT and use their models. I will talk about it a little bit later. So basically what it's doing, so we just create a pipeline which will be transforming this query, this text that we wanted to save into this vector that is understandable by the vector database. And we are basically saving the data into our database. So we just transform this text. We can generate ID. Maybe this is the ID that we'll just take from our relation database. We can provide metadata, which basically means that we can provide anything there. I just provide the original text, so it's return for the user, but there could be like the whole object with all of the other data or ID for the possible answer for this text. And we just save that into the database under the values field, which basically takes this vector and just puts that in the array and save that into the vector database. If we want to just initialize those, so basically that's as mentioned, like basically it's very similar. So Pinecone provides us the SDK with the Pinecone client. When we just initialize the connection, we just use the index method, to which we provide the index name. So basically that means this is the more or less the index that we wanted to look for. So depending on what data we are storing to that, we can access this kind of, let's say, searching by this index. And there is this method chunk upsert, which basically means that we can, using this method, providing with the index, so connection to our Pinecone database, vector database, we just provide this embedding structure, which basically triggers what we know as an insert in our it's called insert in vector relation database. We just basically save that data to the vector database. In case of the searching, so when we want to search for the elements, so this is the difference in case of relation database. So in the relation database, we just execute the search. We just provide the basically the query and what we wanted to look for. But basically, we just provide exactly the same what user provides usually. But in case of the vector database, because all the data is saved as a vector, so before we actually make the query, we have to make the same operation that we done before adding these elements to the vector database. So we need to perform the same operation. So we have to provide what user wrote into the vector, and then we can finally execute the query. So in case of the Pinecone, we just provide the vector. We can provide the parameter, which basically means how many results, best results, should be returned. This is the stop k. And we are asked if you wanted to include the metadata. So it can return just the results or return results with the all metadata that we saved into the vector database. So this comes a difference between searching for in case of the relation database and vector database, and that if we look into the relation database and we have these indexes, so we basically add an index to the table and we can use that. But in case of the vector database, if we just prepare the data in a specific way, say that using, for example, ChatGPT model 3.5 turbo, and we wanted to right now switch to the, for example, 4.0 because we have had access to that, we basically have to rewrite all the database, because embedding this value using the different algorithm will return us basically or no results or very strange results, completely not what we are expecting. So in my case, using this Xenova, so if I run a query, so ask on my vector database, who is the Batman, and I'm asking for 5 best results, so it will just try to find the closest question. So the first one is who Batman. So as the same, like I ask who is Batman, but I have like normalized question written that is who Batman, and as you can see, it is returning also the score, which basically means how much close our vector database think that result is close to what we wrote down. The second and the third, I think that they're duplicated. Who is having the Batman of India? I don't know what it's called. But as you can see on the fifth, who is the best Batman sidekick and why? So yeah, it's finding a strange question that I have stored in the database, but still it's returned us the some results with the score. And based on that, we can also always make a decision if the score is sufficient enough for us, or maybe we should ask additional question. Okay, can you tell us something more, and just ask for additional question, and then somehow connect this to questions, and then just receive better query and better results. So just some key takeaways. So when maybe you should consider choosing the vector database when you need. So when you need a similarity search, as you can see, like you can try to find that. You have to adapt the model, and that will be the best for you. You can always start with the ChatGPT models, so the GPT 3.5 or GPT 4.0, because there are general purpose, but there are different models also available, which will be more, which could be more prepared for your use case. Of course, grouping similar data, the same. If you need a constant time of insert and remove, and you don't want to recalculate all the indexes in the database, and of course, like effective search in the huge data sets. If you have like this small database, so usually, you can use just Sphinx search or Elasticsearch. Maybe they will be returning different, slightly different results, but like this vector database is always like considered for a huge data set, and that we just need to work, let's say, on the live level, and we don't want to wait for a data factory to just aggregate all the data and just prepare that in some way. And this is like the sources that I used for this presentation in case of the images and some background. And yeah, that's all from my side. I'm Kacper, and I was ex-project manager, and right now I'm working in RST. And if you have any questions that you can't ask right now, you can connect to me on LinkedIn, and we can have a talk. Thank you.
Thank you. That was good. Let's take a seat. Okay. So there's some last-minute questions.
Okay.
Can you give some real-life practical example use case of vector databases other than search?
Other than the search, like it's always connected with the search. Like I have like the example from project that what we are working on. So we have the situation that we are using the third-party data as a, let's say, source of truth, and we need to ask that every time to get the data. But after that, we have to aggregate the data. Like maybe not. It's more about we get the data from the one source, and then we have to filter out, unfortunately, on our side, because based on what other POIs are in the, okay, maybe I will talk a little bit more detail. So basically, we have to search for the search for the elements on the map, and this data is basically not paginated because, like the third-party provider that give us this data, they are not paginated this data at all. And we have to like take this whole data and then filter out on our side to receive the information which of this data has POIs close to that, like McDonald's or Starbucks. And we have to like filter that on our side based on the IDs of this main queries that we stored in our database. And it was very inefficient, like as you can imagine, when we have to like browse for 20,000 records and just filter out in basically in the memory. So we use the vector database to just access that to receive this kind of filtering on their side, because based on the geospatial data that we prepare the model for that, we just filter out this data in a second, basically.
Okay, yeah, makes a lot of sense. On the opposite end of the spectrum, can you use vector databases in place of normal SQL databases for storing user data?
Yes and no. Like I wouldn't use that as a primary database. Still, depending on the use case that you have, it will be a relational or no relation database. Because the primary access to the vector database is always, this data is saved as a vector. So it's not like we can access easily the data of the user by the ID, because we have to like perform the query. So like I wouldn't use that as a basically primary database. It's more about additional database that we can use as a search, helpful for searching for these large databases. But depending on the use case that you have, for example, the Postgres has the plugin that can simulate the vector as one of the columns. So you can always use that one to basically reduce this time of waiting for the request to basically outside the service that it always has to be considered.
Okay, thank you. And sorry to put you on the spot, but why do you have so much data on Batman? Are you the villain?
No, like I use this because the Pinecone itself has the example monorepo and monorepo. They have the example repository where they have this CSV, and yeah, I just use that. It's like containing 200,000 records. I just ask about the Batman to not ask about the highest building. So yeah, that was
okay. Yeah, that's a very good cover up. Thank you.